Hello. In this part of lesson 1, we will start discussing the case of moving objects. In fact, the first part of physics, which is called dynamics, is the study of motion. Now, what does motion mean? How do you know if an object is moving? Is there any way to tell if one object is moving and another object is not moving? What is the test of motion? Alright, let's have a look. Well, we see moving objects all around us and we think we know what motion means. Do you really know what motion means? Alright, consider a football player running with a ball. Alright, the question is the ball moving? The football player has the ball on him and he is running. Now, is the ball moving? Well, it depends on who looks at the ball and from where. Now, the runner, the football player, looks at the ball and says, "The ball is with me, I don't see the ball moving." Does he see the ball moving? No, but a spectator on the gallery says, "I can see the ball moving. I saw the ball was at this point some time ago, and after some time I saw the ball at another point." The only way the ball can change from one point to another point is that it moved. So, you see, the football player looks at the ball and says, "I don't see it moving." But a spectator looks at the ball and says, "Yes, I saw it moving." Now, an object may appear to be moving to one person, whereas it may not appear to be moving for another person. Now, when you sit on your chair, you say that you are not moving. But suppose there is a person on Mars. What does he see? He sees you going around the sun at a neck-breaking speed. He says you are really moving. Then the spinning of the earth makes you go round and round. You are actually moving. But you say you are not moving. Now, is motion a complicated phenomenon? Well, you see, motion is a complicated phenomenon. I want you to have a look at an animation. I will be showing you many animations and illustrations, and all of them are taken from the web. I would like to acknowledge here that none of them belongs to me. They are all taken from the web, which are available for public, and they are available for use in the classroom. So let's take a look at one of them. This animation is taken from NTNU website. I want you to watch the various objects in motion here. There is a river flowing down. There are boats in the river, a raft in the river which is not powered. The boats are powered. These are simply rafts which runs with the river. There is a man walking on the river bank. Now look at the river bank. There are bushes and plants on the river bank, and if you look at them, you know if the bank is moving or not. So there are many things moving in here. Alright, now we are looking from outside and see all these things. Tell me, what will be the kind of motion you will see if you jump into the river? If you look from the river, what all you need to do here is take your mouse into the river and click there. Well, you can see, I am now looking from the river. What do you see? The river bank is moving backward, and the boats seem to have slowed down. And what happened to the raft? The raft is at rest. Can you tell me what's happening here? Some time ago, when we looked from outside the river, we saw the river moving, the river bank at rest. Now when you look from the river is at rest, the river bank is moving backward. Where's the man going? You see, the person on the river bank is moving west now. Previously he was moving east. Alright, now tell me what happens if I go and observe from the boat. I'm now going to go into the boat and see what happens now. When you look from the boat is at rest. The river bank is now going backward at a tremendous speed. Look at the river. What is the direction of flow of the river now? The river is flowing backward. Isn't it amazing? Motion is such a crazy thing. You see? So, who is moving and in what direction depends on who looks from where. Alright, let's go to the river bank and look from there. Can you tell me, what do you expect when you look from the river bank? Alright, let's go to the river bank. There you are. When you are on the river bank, you see the river bank at rest. The man on the river bank is moving east. Can you see him moving east? Well, he will come on the screen very soon. There he is. He is moving east. On the boat, the river is flowing down. You can see those yellow things there. The boat, you can see the raft. The motion of the raft actually indicates the motion of the flow of the river. Okay, now, did you get it right? What happens if I now go and sit on the shoulders of the man and then observe from there? In other words, make that man the observer. There you are. The man is now, I'm looking from the shoulders of the man. What do I see? I see the river bank going west. Well, I see the river flowing, well, not as fast as it was before. Is that right? And the man is now at rest. Okay, I think I'm going to leave it for you to play around with. This is a very interesting phenomenon to study motion. What does it tell you? It tells you that motion is relative. It depends on who looks at from where. This now leads us to the concept of frame of reference. Well, the motion of an object depends on who the observer is and where is the observer stationed. What is a frame of reference? A frame of reference is where the observer is stationed. When I look from here, I'm in the classroom and I see all my students sitting on their chairs. And I say, from the frame of reference of the classroom, my students are at rest. From the frame of reference of the classroom, my students see me walking. You see that? But from the frame of reference of the planet Mars, my students are moving. You see, frame of reference is a place from where you make observations. In the frame of reference of the river bank, the person is moving to the right. In the frame of reference of the river, the person is moving to the left. Now, what is the motion of the river when observed from the boat? You remember when observed from the boat, what is the motion of the river? You saw the river moving backward. In the frame of reference of the boat, the person in the river bank is moving west. But the person on the bank says he is walking east. Now look at the confusion here. the person on the riverbank says, well, I'm walking east. But a person watching that person on the bank from the boat says, no, you are going west. Who is right? Well, in fact, both are right. They are right in their own frames of reference. So an object is at rest or in a state of motion with respect to a reference frame. In order to study the motion of an object, we need to define the reference frame. That is very important. An object observed to be at rest in one frame of reference may be moving when observed from another frame of reference. Well, that brings us to the question of change in position and displacement. You see, no matter where you observe from, if you observe an object in motion, that moving object will change its position. All right? A moving object changes its position, and we're going to call that position x. You see, a motion can be in the x direction, in the y direction, or in the z direction. Now, very often we consider motion in the x direction, so we will represent the position of an object using x. On the other hand, if you consider objects moving in the y direction, then we will replace x by y. That means when you represent the position of an object, x can be replaced by y depending on if it is moving horizontally or vertically. So we will represent the position by x and time with t. The position x changes with time t. The position is a function of time. That means we can now write an equation for the position function, can't we? Now, here we have an object in motion. You can see again an animation which is taken from an open web. Now, an object is in motion. Its position changes with time. You can see as time changes, the position changes. Now, let's take a specific example. The position x of the car changes with time t. Let the position of the car be x1 when the time is t1. Alright, here I'm going to put a car. There is the car. Its position is x1 when the time is t1. And the car is at x2, there you are, when the time is t2. Alright, so you got a car at position x1 when the time is t1. The car is at position x2 when the time is t2. What is the change in position? The change in position is the final position minus the initial position. x2 minus x1. And we will represent that change in position by the notation delta x. I'm sure most of you know this. A change in any quantity is represented by using the letter delta. Delta x is the change in x. Delta y is the change in y. Delta t is the change in time, and so on. So the change in position of the car is x2 minus x1 equal to delta x. Now, this change in position occurred in what time? It occurred in the time t2 minus t1. And now, I want you to watch this statement I made. The change in position of a moving object is called its displacement. You see, the object got displaced from the initial position to its final position. So this delta x, the change in position, is called the displacement of the car. This change in position delta x occurred in a time interval t2 minus t1, and we will represent that by delta t. Alright? Now, delta x divided by delta t is called the average rate of change of position. Delta x divided by delta t is called the average rate of change of position, and we call it the average velocity. In other words, average velocity is the rate of change of displacement with respect to time. You see that? Displacement divided by time is a measure of the average velocity. Well, now let's distinguish between average speed and average velocity. What is the difference between speed and velocity? Let's assume that the car moves from point A to point B along a curved path. This is the car which is originally at point A, and it moves to point B along this curve. I think that has gone out of the screen, but the car is over here at point B along this curve. Alright? The length of the path is the distance covered by the car. Look at that, the car went along this path, and so S is the distance covered by the car. Now, the rate at which an object covers a certain distance is called its speed. So speed is the rate of change of distance, the rate at which an object covers a certain distance. In other words, average speed is distance covered divided by time, that is S divided by t. This is S divided by the time taken. What is the unit for measuring average speed? Distance is measured in meter, time is measured in second, it is measured in meter per second. But now tell me, the object, the car moved from A to B. What is the change in position of the car? What is the change in position of the car? The net result is that the car moved from position A to position B, and therefore the displacement of the car is the shortest distance measured from A to B, and it has a direction. Watch this. This is the displacement. It's the shortest distance measured from A to B, whereas the distance traveled is the length of the path taken. Displacement is the shortest distance measured from the initial position to the final position. Now you notice that displacement has a direction from the initial position to the final position. There you are. Displacement delta x is the shortest distance measured from the initial position to the final position. And therefore, the average velocity is the rate of change of position. The average velocity will be the rate of change of displacement. It is delta x divided by delta t. Whereas the average speed is the distance covered divided by time. The average velocity is the rate at which the displacement is being done. Delta x divided by delta t. Velocity has a direction. So what is the distinction between speed and velocity? Speed simply tells you the rate at which the distance is being covered, whereas velocity gives you two information. What are the two information? It tells you the rate at which the position of the object changes, And also it tells you in what direction is the position changing. So velocity carries two information with it. So you must distinguish between speed and velocity. Let's now talk about instantaneous velocity. What's the meaning of instantaneous velocity? Velocity at a given instant. Now, in the last slide, we defined average velocity or average speed. In other words, it is the velocity in a certain interval of time. We are now interested in finding the instantaneous velocity. What is the velocity of the object at a given instant of time? Often we need to find the velocity of an object at a given instant. Now, here we have, again, we go back to the same example. The object is displaced from A to B, and the displacement is delta x. Velocity at a point can be obtained by making the time interval shorter and shorter and shorter. You see, we want to find the instantaneous velocity, velocity at a particular instant. So what do? Make that time interval shorter and shorter, and making it very close to zero. It cannot be zero, but make it as close to zero as possible. When delta t is made very small, what happens? The point B will come closer and closer to point A. Look at that. This is the path of the object. This is the path taken by the car. And so the average velocity during that interval is delta x divided by delta t. And now, suppose the car is moved from A to B. You bring B over here, and you notice that the time interval is now shorter. If B is over there, the time interval is even shorter. And if B is over here, let me write down those points there. Suppose this is my point B. What I'm doing is I'm making the time interval shorter and shorter. You see, if this is the initial position and this is the final position, then the average velocity is delta x divided by delta t. On the other hand, if this is the final position, the average velocity for that interval will be, this is my delta x, and delta t is now shorter than before. Now, on the other hand, if this is the final position, this is the new delta x, and delta t is shorter now. If this is the final position, delta t is even shorter. That means I'm now getting my point B is coming closer and closer to point A. And I'm very, very much close to defining instantaneous velocity. So what did I do? I make the time interval shorter and shorter so that my interval becomes smaller and smaller. And finally, what happens? When delta t is made very small, then point B gets very close to point A. And finally, what happens is, when the velocity at point A, when B is very close to A, we can then say the velocity during that very small interval can be called the velocity at A, and that will be defined by the tangent drawn at that point. So velocity at the point A is called the instantaneous velocity. So let me come again here. You can see delta x divided by delta t. Can you tell me what quantity that delta x divided by delta t defines? If you come in here, now, if this is my delta t, now delta x divided by delta t is the rate of change of position. We actually call it the slope of this line. You see, the average velocity during this interval is the slope of that line. The average velocity during this interval is the slope of that line. Average velocity during that interval is the slope of this line. So what are we doing? We are making the interval shorter and shorter. The average velocity during this interval is the slope of this line. And finally, when you come to point A, we don't have a secant line anymore. You can see all these are secant lines. At point A, we have a tangent line. And therefore, the instantaneous velocity at point A is the slope of that tangent line. Whereas average velocity is the slope of the secant line. The instantaneous velocity is the slope of the tangent line. And it is a measure of delta x divided by delta t when delta t approaches 0. When delta t approaches 0, point B almost comes and joins with point A. And the velocity at point A then is the slope of the tangent line. I hope you understand that concept. It's very important to understand that concept. Alright, let's move on. Therefore, instantaneous velocity, V instantaneous, is defined like this. It is the limiting value of delta x divided by delta t. You understand the meaning of limiting value. As delta t is made smaller and smaller and smaller, the limiting value of delta x divided by delta t is called the instantaneous velocity at that point. And therefore, it is the slope of the tangent line at that point. And those who understand calculus will call it the derivative of the position function. If you are not doing calculus, you don't need to worry about it. But understand it as the velocity at A, the instantaneous velocity at A, is the slope of the tangent line at that point. Okay, I think I have an animation showing that concept. Here, you can see delta t gets closer and closer to 0, and the secant line becomes a tangent line. Average velocity in an interval becomes instantaneous velocity at a point. You see that? The slope of the secant line is a measure of the average velocity. And tell me, when does the average velocity become the instantaneous velocity? When the time interval is almost 0. When point A and point B are almost one on top of the other. You understand the difference between instantaneous velocity and average velocity. It is very important to understand that concept. Therefore, if you draw a graph of displacement against time, in other words, position of the object, draw a graph of position on the y-axis and time on the x-axis, then the velocity, if the velocity is a constant, you will get the graph a straight line. And the slope of that graph will give you the constant velocity. You see, if the velocity remains a constant, then only the line will be a straight line. So, displacement against time will be a straight line if the velocity remains a constant. And the slope of the displacement against time graph will be a measure of the velocity. On the other hand, if the graph of displacement against time is a curve, then the velocity changes from point to point. Here you have the velocity changes from point to point, and watch this carefully. If this is my point A and this is my point B, then if I draw the straight line there, this will be called a secant line. The average velocity between these 2 points will be the slope of the secant line. And in order to define the instantaneous velocity, what do? Bring points A and B closer and closer so that this delta t is very close to 0. And then the limiting value of delta x divided by delta t will be then the slope of the secant line, the slope of the tangent line at that point. You see that? Instantaneous velocity is the slope of the tangent line. Now understand the difference between average velocity and instantaneous velocity. Okay, I think we can now use these concepts to solve problems. Before we start solving problems, I would like to demonstrate to you the difference between average velocity and instantaneous velocity. What I'm going to do is I'm going to run this car from an initial position given by this photo gate to the final position given by this photo gate. Now, when the car, you can see I have placed a little splinter here. When the car moves through the photo gate, it will disturb or block a beam of light that will then start this clock. And when the car reaches the second gate, this clock will stop. In other words, it will measure delta t, the change in time. And we know delta x. And if you know delta x and delta t, we can find the average velocity. Is that right? Now, I have put delta x as 60 centimeter, that is 0.6 meter, and I'm going to run this car. What I'm going to do is I'm going to use a car, well, I'm going to launch the car with this. This is like a gun. I can shoot the gun in motion. I'm going to load it and I'm going to shoot the car, all right? Okay, watch what happens when I shoot the car. The car is, well, let me see if I can shoot this car properly to behave, all right? I may not get it go in the straight path, but then I will have to repeat it, all right? I'm going to shoot the car now. There you are. So, well, apparently the clock didn't start. Is that right? Well, I'm going to make a third attempt and see if the clock responds. All right. Now, what does that time interval tell you? 0.0169 is the instantaneous rate of change. In other words, this is my delta x that is very small, and this is my delta t, which is very close to 0. So the instantaneous velocity will be this time delta x divided by delta t, where delta x is the width of the splint and delta t is this. Is that right? So you can see we brought the interval closer and closer, making delta t very, very small. And now we made that delta t so small that during that delta t, the displacement is only the width of the splint. That means A and B are almost on top of each other. This is the meaning. Limit delta t approaches 0, delta x over delta t is the instantaneous velocity of the car. Now, let's see if I move the car in there with the splinter, we can measure the instantaneous velocity. And there you got. Now, the width of this is about 0.5 centimeter and the time taken is 0.0107 second. So what is the instantaneous velocity here? I'm going to leave it for you to calculate. Well, I hope you got some idea of the difference between average velocity and instantaneous velocity. A simple problem. Well, the problem goes like this. The position of an object is given by the function x of t equal to negative 4.9 t squared plus 15. What is the velocity of the object 5 seconds from the start? At the instant when the time is 5 seconds, what is the velocity? We are looking for instantaneous velocity. Now, what is the definition of instantaneous velocity? Instantaneous velocity is the limit when delta t approaches 0 of delta x divided by delta t. And this is what we call the derivative of the position function with respect to time. Is that right? So, velocity, instantaneous velocity is the derivative of the position function with respect to time. We are given the position function and we need to find the instantaneous velocity when time is 5 seconds. So what all you need to do is find the derivative of the position function and in that derivative set t equal to 5 seconds. Alright, let's do that. Alright. Instantaneous velocity is the derivative of the position function. What is the derivative of this function? X of t is negative 4.9 t squared plus 15. The derivative of this will be dx by dt, use the power rule, negative 9.8 t plus 0. Or the velocity at any time is negative 9.8 t. And we want to find the velocity at t equal to 5 seconds. So v of 5, velocity at t equal to 5 is negative 9.8 times 5. That is negative 49 meter per second. Now you can see the instantaneous velocity contains two information. What are the two information? The rate at which the position changes is 49 meter per second. Every second its position changes by 49 meters. Also it tells you the position changes in the negative x direction. So it tells us that the object is moving to the left. Moving to the left. That is the negative sign. The two information. Well, what I'm going to do again is to stop this lesson, this part, the second part of the lesson here, and do a third part. That will be all solving problems. Alright, I will see you for that in a while.